In the mid-1905, Albert Einstein derived what is now the most famous equation in the world, E equals mc squared. But he didn't just write this down out of the blue. It followed directly from his paper on the special relativity. And now, here's how he did it. Suppose you are watching a cat float freely in an empty space when suddenly it emits a flash of light in all directions. The light carries away some energy, we call it as E. So by conservation of energy, the cat must have lost energy E. But since light was emitted symmetrically in all directions, it won't have changed the cat's velocity. So where did the energy come light from? Never mind, that's now. Let's imagine you get bored and zoom in if in a spaceship in the middle of the experiment. But from your new perspective, you are sitting still in your spaceship and the cat is the one who's moving past outside the window. Therefore, you will calculate that the cat has some kinetic energy that is energy of motion, and when you see the cat emit the flash of light, you will again measure that its energy decreases by the time of the light. Except now that you are moving, special relativity tells us that time passes at different rates for you and the cat. So you will measure a different value for the frequency and thus energy of the flashlight. This is the relativity Doppler effect, and for our purpose, it amounts to multiplying the energy of the light by 1 plus your velocity squared divided by twice the speed of light squared. So to recap, if you take off the velocity v, you will see the cat gain some kinetic energy, Ke1. Then at the flash you will see the cat's energy decreases by E times 1 plus V squared over 2C squared. On the other hand, if you wait, you will see the cat's energy decreases by E. And now, when you take off, you will see it gain kinetic energy Ke2. But this is still, you never touch both, you never touch or otherwise influence the cat in either case. So you should get same total energy at the end. Rearranging, we see that the kinetic energy before and after the flash must be different, and the kinetic energy of an object is 1/2 of its mass times velocity squared. But now, then that the velocity was the same in the both cases. So in order to account the difference, the cat's mass must change when it emits the light flash of light. Now, if we cancel things out, you can see that the change in mass of the cat must be equal to the energy divided by c squared, or as you have heard before, E equals to mc squared.